Okay, um, so uh, good morning or good evening or good afternoon, whatever it is for you. Um, this is Dylan King, and today is April 21st. And if this goes well, this will be a recording of my presentation for Math 732, my project. And I'm doing this on Zoom, and I've never recorded anything nearly this long by myself on Zoom before. So I'm going to be sort of feeling my way through the dark on technical difficulties, but I think everything will bear out. And so without further ado, we're going to start with this PDF, which we're going to sort of focus on, and then I'm going to sort of swap to the whiteboard so that I can draw some pictures, and also swap briefly to an exciting surprise that I think you will enjoy. Okay, so if I understand correctly, right now you can see the same PowerPoint slides that I can. And so, okay, we got the title, my name, and the date. And the topic that I'm going to be talking about today is map colorings of surfaces. Um, and so this topic, to me, at least as an undergraduate, lies at the interface between combinatorics and discrete mathematics and topology. So this vast world of continuous shapes living inside ambient spaces and the discrete structures of graph theory. And so, as in the title, this talk is a lot about colorings. And so I know that not everyone can see all of the colors as well, but I think I've tried to make everything pretty visible. So, okay, without further ado, so we gotta get rid of a few essential definitions. All of the topology we're gonna need for this talk, we've already covered in class plenty enough. But like I mentioned, there's a decent amount of combinatorics involved, and so we're going to need to cover that relatively quickly. These definitions, so just sort of a word of forewarning, to me, graph theory is supposed to be fun. And what I mean by that is the questions in graph theory are supposed to be interesting and exciting. And so the definitions are simply built to keep those problems interesting and exciting, but sometimes they can be painful. And to give you an example of that, so let's just start with our first definition. And I apologize to anybody who is already a combinatorics expert, but I know that not everybody is, and this will be a pretty brief introduction, so I think we can all enjoy it. So a graph is just going to be a collection of vertices V and edges E, and the vertices are just going to be some collection of objects, and the edges are going to be a subset of the pairs of the vertices. Now, what I mentioned earlier about notation, okay, so I'm going to use the word graph. In reality, there are a bajillion different flavors of graphs. So you can have normal graphs, you can have directed graphs, you can have simple graphs where you allow the edge to go from one vertex to itself, or you can forbid that and not allow an edge to go from a vertex to itself. Or you can do, well, could I include multiple copies of the same edge? So could I go from one vertex to another multiple times? And so when I say that graph theory is supposed to be fun, I'm going to say I'm not trying to say that this is like the be-all, end-all definition of a graph that everybody needs to use. This is just the one that we want to be using. And for our purposes, yeah, we're going to be thinking about directed graphs. We're not going to be doing anything fancy there. Okay. I think the degree of that vertex is just going to be the number of edges which come out of that vertex. And don't worry, you haven't seen graph theory before. A lot of these may not make a lot of sense, but I'm going to switch over to the whiteboard in just a second and draw pictures for all of these. A path is going to be a list of vertices so that all of the vertices are distinct and we have an edge in the graph between each of them. A cycle is a path that closes up on itself. And the girth of a graph is the smallest length of any cycle in that graph. Okay, so now, so let's once again test my technology and see what I can do. So when I say the combinatorics is supposed to be fun, I'm saying that really these definitions are only meant to formalize ideas that you probably already understand. So when I say vertex, I'm going to think about that as a point. That is a point in space. And so I'm putting down a few points now here on this whiteboard. And then an edge, it's just going to be a line that we're going to draw from one vertex to another. So if this is vertex A, B, C, D, E, and F, this edge right here, this is edge BC. And again, because we're not worrying about directed graphs, this is the same as edge CB, et cetera, et cetera. And we are not allowing an edge to go from C back to itself. That's a big no-no, so I'm gonna erase that. And so this is our graph where the edges are lines, the dots are vertices. And the degree of a vertex is simply gonna be the number of edges that it's connected to. So in this graph right here, D has degree 2 because it has 2 lines, B has degree 4 because it has 4 lines, et cetera, et cetera. Now, I also mentioned paths. So a path is going to be a sequence of distinct vertices with edges between them. So I could do the following, so I'm going to switch to lavender. So I could do the fall, I'm going to trace it out and then erase it because I don't want my graph to get too messy. So if I want a path from C to E, I could start here at C, and then I could go up to A, and then I could go across to B, and then I could go up to E. That would be a path from C to E. But it's not the only path from C to E, right? I could have gone from C up to B and then up to E, or I could have gone from C up to A, up to D, down to B, and up to E. And there's no rule a priori that a vertex necessarily has to have any edges connected, right? So this F out here, it's just hanging out by himself. That's okay. That's allowed in my graph. I also mentioned cycles. And these may seem like a little bit of funny choice of graph theory definitions if you know a little bit about dramatic theory, but we're going to need them later on. And so a cycle is just a path that closes in on itself. So I could have a cycle from C to A to B and then back to C. That would be a cycle of length 3 because it's got 3 vertices. I could also have done from C to B to D to A to C. That sounds good. But, right, if we look at this for a second, we notice that E isn't in any cycles because you can only use these edges once. So if I go from E to B to C or A or D, I can never get back to E. And so this is going to be a problem, and that doesn't count as a cycle. And so just to clarify again, one of the definitions that we had on the slide, right, the girth of a graph is the size of the smallest cycle in it. And if there are no cycles, the girth is infinite. So just, quick check of your own definition. So what's the girth of this graph? Pause the video for a second. Okay, so the girth of this graph is going to be 3 because we have all of these triangles here, and that's the smallest cycle present in this graph. Now, you could also, right, so here's, for the sake of argument, if I cut out this edge from A to B, what's the girth now? Now the girth is going to be 4 because the smallest cycle has 4 vertices. Okay, so I'm going to cut away back to the slides, but I'm going to keep these pictures that I'm drawing in case you want to use them for anything. And yeah, and so they're going to stay, and you'll get those two with my slides. So now if I can move this thing so that I can go, okay, back to my, okay, so now we're back on the slides and I've gone through these definitions. And so this is just a crash course in graph theory that we're gonna need for topology later on. Oh my gosh, but there's even more graph theory. And this is where we really start to get into the fun side of graph theory, okay? So a proper k-coloring of a graph is gonna be a function that goes from the vertices to the integers 1 through k, so that if 2 vertices, vi and vj, are adjacent, then the colors, that number between 1 and k, are different on those 2 vertices. The chromatic number of the graph is going to be the smallest number, k, for which a k-coloring exists. Okay, so this certainly deserves some pictures drawn. And so, okay, back to my whiteboard. Okay, and I think you can still see my old drawing, so that's good. Okay, we're gonna open up a new guy. Okay, so let's take a graph, and I'm gonna do something pretty simple. And so, of course, there are no colors in the definition of coloring because that would be too boring for math. That would be too exciting for math, excuse me. But really the motivation here is, and because I'm sure this is a situation that we've all been in, you have a complex pattern on your kitchen sink and a few buckets of paint and an incredibly strict mother-in-law who says that you need to paint the pattern on the kitchen sink using as few different colors of paint as possible. And so what I mean by that is, let's say that this is our graph, right? And so our rule is we need to try and assign a color to each of these vertices so that different vertices that are adjacent have different colors. So let's say that I paint this first guy green. Okay, so he's going to be green. And now my question is, what can I paint this guy here in the middle? Well, I cannot give him the same color. I cannot give him green because his neighbor over to the left was already painted green. Okay, so green isn't going to work, so I'm going to go for this ocean blue. So the middle guy is going to have ocean blue. Okay, now I look at the third vertex and I say, gosh, what color can it have? Well, it definitely can't have ocean blue, so maybe I'll give it, this is a nice orangey color. Okay, so here's orange. We've got green, blue, and orange. And if you wanted to, you could think about these as the integers 1, 2, and 3, because we're using 3 different colors of paint, right? So we've got, this is a 3 coloring of this very, very simple graph with just 3 vertices and 2 edges. But your mother-in-law is extraordinarily unsatisfied because clearly you're wasting her paint, right? You've used 3 different colors of paint. And remember, right, so this is a good 3 coloring. Remember, the chromatic number of the graph is the fewest number of colors so that you can find a painting, right? So what that means is that we've shown by this example that the chromatic number of this graph is at most 3, because you can paint it with 3 colors. The question, however, that your mother-in-law so desperately wants you to know is whether or not you can paint it with just 1 color, or just 2 colors, excuse me. And the answer, as you can probably guess, is yes. This last guy, we used orange. There was no reason to use orange. We can easily recycle, if I can pick up my pen again, we can easily recycle green and use that on the last guy, no problem. Now this is a 2 coloring. It's obviously not 1 colorable, right? Because if we only had 1 color, then the green guys and the blue guy, they would get the same color and we would run into a problem. Okay, so this is just a demonstration on what the chromatic number is and what a K coloring is and how these things really come into play on a graph. Now you can imagine as the graphs get bigger and bigger, this question might get more complicated. And by complicated, I mean fun, right? Graph theory is an exciting field. But with that, we're gonna come back to our slides. Okay, so here are the definitions that we just reviewed. Okay, and so here are just like some questions, right? Some fun questions that we can ask about graphs. So if I have a number n, is there a graph with chromatic number n? So is there a graph that requires exactly n different colors of paint? And the answer, of course, is yes, that's a complete graph. And a little bit of intuition that we can think about here is that this chromatic number is going to be monotone. And what I mean by that is that if I have 2 graphs that work on the same vertex set, but one has more edges than the other, and by more, I mean set-wise containment, right? Not some sort of weird counting thing, then that thing with more edges can only be harder to color. And so let me give you some brief pictures to demonstrate what I'm talking about. So first, just in case you haven't seen it before, because again, not everybody loves combinatorics. So the complete graph is, so here is the complete graph on 3 vertices. You draw 3 dots, and then between each dot, you draw a line. Now, what's the chromatic number of this thing? So it's definitely 3 colorable, right? Because I can go in here, and so now I'm going to switch back from colors to numbers because I'm trying to do this fast. So I'm going to color this one 1, this one 2, and this one 3. No 2 adjacent vertices have the same number. Good, it's a coloring. Sounds good. Is it 2 colorable? Well, if it's 2 colorable, then if we color this first one with color number 1, then we got to color the second one with color number 2, and then, uh-oh, your mother-in-law is out of paint for the third one. There's nothing left, right? We can't color this one because it's upper neighbor, and we can't color it 2 because it's the other neighbor, and so we're out of gas. So this one, so chi of this guy is 3, and we call this graph, this is K3, because it's a complete graph on 3 vertices. Now I can do the same thing for 4 vertices, right? So I draw 4 dots, and then I draw all the connectors like this. And so now I ask what the chromatic number here is, and using exactly the same thought process, this is going to be 4. And so if I ask for the chromatic number here, and in general, the chromatic number of Kn, it's going to be n. So if I can find a graph that has n vertices and all of the edges are all linked up, then I'm going to need at least that many different colors for all the different vertices because there are so many edges. But that other thing that I was talking about is I think about, geez, what if I had a really big, complicated graph and had a lot of vertices and I wasn't really sure what the chromatic number was, but I knew it was something because it's a well-defined object. And so maybe this is my graph and I say, okay, this is a graph and I know its chromatic number. What happens when I add in another edge? So I'm gonna add in, maybe I'll do it in lavender because that's a fun color. I'm gonna add in this lavender guy up here. So what's happening? I've only forbidden more examples, right? Your mother-in-law can only get less happy with this new picture because maybe it's possible that the painting scheme that you used for the old graph still works, that these two circled vertices, they had different colors of paint, and so everything is peachy. Nothing has changed for the chromatic number. But it's possible that when we added this edge, we caused a conflict. That the only way you could solve the old problem was by making these two corner guys the same color. And so by adding this edge, you have ruined everything and we're out of luck. And so this is just some intuition about chromatic number. The more edges, the higher that thing is going to go, up to the number of vertices if you have all the possible edges. But if it's really few edges, right? So in the extreme example, what if we just had something really simple, like back in the Roman times, just good old roads, right? Just straight lines, a line graph. Oops. If I had something like this, well, what's the chromatic number of this thing? Oh, that's easy. This is just going to be 2, right? Because I can go through here. Okay, so let's call the first guy. Let's color the first guy with 1. Then I color the second one with 2. And then I color the third one with 1 because he can't be 2. And so it has to be 1. And then this fourth guy, oh, well, he can't be 1. So it's going to be 2. And then we just continue to alternate down the chain. So if we don't have many edges, the chromatic number can be really low. Okay, now back to the slides. Okay, back to the slides. Okay, so here's just a little warning because it's going to scare you. There's a super formal definition on its way. Okay, a graph is planar if I can draw it without the edges crossing. And so, of course, like I said, graph theory is supposed to be fun. We can state this with like embeddings that don't intersect and all of that jazz, but it's not very fun because the definition is, as it's written, maybe is not totally formal, but it's definitely very clear on what it means. And so now we're going to cut back, and I just want to show you a really quick example of a graph that is and is not planar. So let's take something. Let's take K4, so the complete graph on 4 vertices. Is this guy going to be planar? So I want to ask, can I draw everything so that there are no overlaps? So I'm drawing. Okay, so I got this square, and I got to connect these corners, right? So I can put that line in here. And last time when I drew K4, I just cut across. Ooh, that's bad news because these two lines crossed. Okay, and so the question is, can I get from over here to the other side without crossing? And right away you say, oh yeah, no problem. Perfect, bingo. So K4 is a planar graph because I can draw it like this. Now, we could ask the same thing about K5, right? Maybe we could just keep going up and everything stays planar. And so maybe you've seen this before. I don't want to spoil the surprise, but it turns out that K5 will not be planar. So let's try the same thing, right? So I can put one diagonal in there and I can put the other diagonal in there, right? And then, so I have a little bit of walking to do, right? So I have to walk from these 2 on the left to these 2 on the right. So maybe I go this way for this guy. But now these 2 vertices I'm about to circle in red, there we go, they can't talk to one another. And so this isn't an entirely formal proof, right? But it's just a demonstration of why this thing won't be planar. And what we're going to try and think about while I go back to the slides is this planarity condition. It forces you to have fewer edges than you might otherwise, right? Because the lines have to be able to cross. And so maybe, right? If G is planar, then I can say something about the chromatic number of G because there's going to be fewer edges because those edges aren't allowed to cross. So maybe chi of G will be small. And it turns out, this is a very famous theorem, so maybe you've heard of it. It's called the four-color theorem. It's Appel-Hawken in 1976. Used some computers, so it's very nice. If G is a planar graph, then it is four-colorable. And so just to sort of reiterate what this means is that if we take one of those graphs that we just drew, then I can four color. Maybe its chromatic number is a little bit lower, but it's definitely no bigger than 4. And this makes sense with the examples we saw, right? So we looked at K5. We said K5, it's definitely not planar. Oh, but it's not four colorable, right? So it's not a counterexample to this theorem because it's not planar, but it does require 5 colors. We also saw K4, right? K4 is planar. So according to this theorem, it better be four colorable. And yes, as we talked about earlier, it is four colorable. So everything sounds great. And I can't really show you the proof of this because it's pretty complex. The 5 colorable theorem is pretty straightforward. But this one is a little bit more advanced. Okay, but we're going to do a transition now because so far we've really only been talking about combinatorics and graph theory, right? There hasn't been a lot of topology going on, but we're going to get there, I promise. And the route that we're going to get there is through maps. So if I gave you a map of the United States and the rule that no two adjacent states could be the same color, how many colors would you need to color in the whole thing? So if you want, you can look up a map of the US and pick up a couple crayons. I have tried this exercise. It's phenomenally hard. And if we look at this thing, okay, so here's one map. And maybe, I mean, one of you guys can maybe count the colors, right? I mean, I can see like 7 or 8 right off the bat, right? It's a very big number. And right, the reason that we're sort of, in a vague application sense that we're interested in this problem is because if I want a good map, I can't have Texas and Oklahoma be the same color. That would just be ridiculous. If 2 states are adjacent, I need them to have different colors. And so I want to talk formally about something important, and that is that when we say adjacent, we really mean adjacent in a substantial sense. That formally, that the intersection of the boundaries of the two is still a line segment in some sense. So I am not saying that the 4 corners that Utah, Colorado, Arizona, and New Mexico are adjacent. Arizona and New Mexico are adjacent because they share an edge. Colorado and New Mexico are adjacent because they share an edge. But Utah and New Mexico are not adjacent because they only kiss at that corner. Same thing with Arizona and Colorado, not adjacent. Okay, but we're trying to find this thing. See, how few colors can I get away with, right? So if I look at this map for a second, let's look at these yellow guys. Are there any colors that none of the yellow guys touch? And I'm pretty sure that if I took that sort of tealy aquamarine thing of North Dakota and I made all of the yellow ones that color, that I would still get a legal color. So I would still have adjacent states distinctly colored. And so that means that I can do better than this. And if you look at, there's so many colors. This is like a rainbow. Surely we can do better than this. And the answer is that it turns out, yeah, if you work at it, you can color the US according to these rules with only 4 colors. And so I'm going to point out again the 4 corners. Arizona and Colorado, same color, but they're not adjacent because they're across from that little point. So that's no problem. And so this is a pretty cool idea, right? That in fact, it only takes you 4 colors to color in a map of the US. And you may recognize that number from earlier in the presentation. But before we get to that relationship, okay, what if this was just the US, right? What if we wanted to do the counties of England? So here's a pretty low resolution map of England, and we got the counties colored in. And if you look at this guy, this is a 5 coloring. So starting in the bottom left, I can see yellow, pink, green, orange, and sort of a purpley guy. And so again, surely, we can do better than this, I think, right? If this is a math talk, there's got to be some kind of pattern here. And the answer is yeah. If we're careful, we can, in fact, 4 color the counties of England. And that was sort of the original problem that brought around this very mathematical question. And so you're probably sensing a pattern here. And it really is a theorem that any map, and when I say map, right, again, this is supposed to be fun, but like the formal definition of a map is a subdivision of your surface into connected regions who are considered adjacent if their boundaries intersect in a line segment. or some one-dimensional manifold. And so we can actually prove this theorem really easily using the graph theory I talked about earlier, just sort of port things from graph theory into topology. Okay, and so how are we going to do this? So the proof, and again, the slides aren't complete because I'm going to be drawing pictures with them, is if you give me a map, I will give you a planar graph. Then you're going to color that planar graph. So let me pull my whiteboard back up. Okay, so let's say I give you a map, and I can do it on this same one because I don't need any, and we'll go and open a new one. So let's say I have a map, and we're going to be boring, and the country or the space they're going to be working in is this big old rectangle, and I'm just going to take it and I'm going to cut it up like this. Maybe there'll be like a little guy in here and some boxy fellas over here, something like this. And the question, right, so here's my map. And if I want to four-color this map again, so that adjacent states or countries have distinct colors, what I'm telling you is that I'm going to get a planar graph. And how am I going to get a planar graph? So I need to make vertices and edges, yeah? So I'm going to put a vertex down here, a vertex down here, and I'm going to put a vertex down inside each of the states. So I'm going to go through here and do this. And now for my edges, I'm just going to put an edge down if the two states are adjacent. Okay, and so I'm not going to do all of them because it's way too much work, but you see the pattern that I'm going for here. And so when I fill all these in, what sort of object am I going to have? Well, I'm going to have a graph, and better yet, it's going to be planar, right? Because the fact that all the edges are between adjacent states means that the edges will never have to cross. So we've already got a planar representation of this graph. So it's going to be four-colorable by that big fancy theorem that we didn't prove, but very smart people have. So we know it's going to be four-colorable. And so what does that mean? Well, that means that I can go through here. So this guy will be lavender, and this guy will be lavender, and this guy will be lavender, and this guy is going to be forest green, and this guy is going to be forest green, and so will this guy. That means I can go through this graph and assign colors to the vertices so that, what's my rule? My rule is that adjacencies don't have the same color. Well, what mean for vertices to be adjacent? It meant that their states that they belong to are adjacent on the map. And so what exactly this means is that this coloring is a valid coloring of that map. So really, we've actually just solved the exact same problem. So now I'm going to come back to my slides because I've demonstrated that proof. And I'm going to show you a really pretty picture of what I've just demonstrated, right? So this is a great one from Wikipedia, just sort of demonstrating how I would go from planar graph to map and vice versa, and how that coloring process would work. Okay, sounds great. But really, there's a little bit fancier thing going on here. So as I draw these maps, right, the last one, I put it inside of a box. And that sort of gives a picture that this is all happening on a plane, right? But really, we can do all of this on a sphere, on S2. And so the reason that I put this graph here is for no other reason that it helps me with a little bit of a visualization. So I want you to take this graph, which is obviously planar, because here's a planar representation. I want you to imagine taking a balloon and putting it behind your screen, right? So there's a balloon behind this graph, and then pushing the balloon towards you through your screen. And so all of these vertices are going to fall onto the balloon. And these 5 that form the outermost pentagon, they're going to be very far back on the balloon, close to where your hand is pushing it towards your face. And so this graph is going to live on this sphere. And so really what we've done is we've taken one country and we've pushed it all the way out. So let me switch. I can switch very quickly. So what this is really doing, what we're really talking about here, is so if I had, and I'm going to be doing sketches here because I can't really draw the Earth that well. So if I had the Earth, and I'm not going to put the countries in because I need to draw, right? And let's say I had some country division of the Earth, and it was super Pangea. There were no oceans. It was just this ball, and so we had all these countries. What I'm doing here is to get this planar graph. Is I'm going to take all of my countries, and I'm going to put these dots down, and then I'm going to connect them up just like I had before. And then the thing that you may be worried about is sort of that there are some dots, right? I've drawn this sphere projected onto this whiteboard, but there are some dots on the back of the sphere, right? Just by the fact that I drew the sphere, and there are countries on the back of the Earth, right? And so the question is, why do I still know that the graph that comes out is planar? And the answer is to take your sphere and to just blow this country up, right? So I'm going to take this guy, I'm going to mark him in lavender. I'm going to take this guy and I'm going to blow him up. I'm going to make him huge, right? And this is topology, so I'm allowed to do that. I get the same kind of object down. And in fact, I'm going to make him so big, he's going to dwarf the US, dwarf Canada, dwarf Russia. He's going to cover the entire back half of the sphere. He's going to fill the whole thing up. But again, because we're doing all this sort of ambiently and smoothly on the surface of the sphere, we're not breaking any of our adjacency relationships. We're just warping the boundaries a little bit. And so now, if I flip this thing over, so if I flip, what I've got here is I've got basically all the countries in the world, but they're squished. They're squished down here. And so oh, and that's not where I wanted to put that lavender. So I got some lavender out here, right? This super countries on the outside, but there's nothing on the back of the sphere. And then this will leave me with a planar graph on the inside. So this really is, honest to goodness, working for any countries that live on the sphere, right? So even though some of the pictures I've been drawing for you make it look like this problem is happening on the plane, really this problem is happening on the sphere. Okay, so that sounds good. But so you notice, right, that sort of we've slowly transitioned from talking about graph theoretic objects. Now we're talking about spheres. Okay, and so here is where things are going to get really spicy. So there's nothing special about a sphere, right? If I have a surface S, maybe I can just call the chromatic number of S the largest chromatic number given by the graph coming from any map on S. So if I don't want to use a sphere, let's take a torus or a two-hole torus or a Mobius band or a Klein bottle, and I cut that thing up into a map. And again, right, I'm avoiding the formal definition of a map because it's not fun and it's not interesting. It's boring. This presentation is supposed to be exciting, right? This map, the countries have to be connected, the states have to be connected, and the adjacency means that they have to have substantial parts touching, right? We can't have a sort of 4 corners or 5 corners or 6 corners scenario. Well, if I take that map, from that map, I can make a graph, right? The same adjacency graph I've been making. So if I take that graph, I can compute its chromatic number. It has a chromatic number. So if I have a random surface, I can look at all the maps that could ever show up on that surface, and I can take the maximum of the chromatic number obtained by the graph corresponding to any of those maps. And I can call that the chromatic number of the surface. So for example, what we've already shown is that the chromatic number of the sphere is 4. Because, right, and it's pretty clear, it's not too hard to make maps that require 4 colors. And using this 4-color graph theorem for the planar graphs, we've shown that if we have a map on the sphere, the corresponding graph will be planar, and then that graph is 4-colorable. So chi of the sphere, that's just going to be 4. But, right, now we're in full-on topology mode. Everybody knows the Earth is not really a sphere. The Earth is obviously a torus, right? This is the picture of the Earth, right? Voyager took this 2 weeks ago. And so the question is, because Earth isn't really a sphere, what will be the chromatic number of Earth? Because it's not a sphere, it's a torus. And so we can, right, again, this is the same question. We still have maps, and the graphs associated with those maps are no longer planar because we can no longer perform the same transition. Okay, but we can still draw those graphs, right? So if I had a map on the sphere and I was interested in what that corresponding graph looks like, so I draw it. Is the graph still planar? Probably not. Is it still 4-colorable? I I don't really know, right? I mean, that's a question, right? Can we draw a graph on the sphere that won't, can we draw a map on the torus, excuse me, can I draw a map on the torus so that the graph of that map will not be four colorable? And so the answer, so let me now, so I mentioned at the beginning of the presentation, a special surprise. Now it is time for the special surprise. Here we go. Okay, I think that this is the most beautiful thing I've ever seen. So this is actually the reason, so here's a brief story. The reason that I decided to do this topic for my presentation was that this last year, before COVID-19, I was at a conference. And the conference, excuse me, like many conferences themed at undergrads, had a poster session. And it also had, and as many conferences do, the poster session was held over lunch. And lunch was this marvelous Mediterranean food. So I was eating my Mediterranean food, browsing the poster session. And they were sort of going on in the same really big room. And I came up to this poster, and the poster had sort of hanging on the easel, someone had knitted something that looked just like this. So it was a knitted torus with all these crazy color bands. And there was somebody standing there. And so I asked him about the torus. I said, "What's going on here?" And he said, "Oh, it's a crazy torus." And then I said, well, okay, what's going, I mean, yeah, sure. But I mean, what does this really mean? Um, and, and he said, "Oh, I have no idea. I'm just here to help to organize the luncheon." Right. He was part of the catering company that had brought the Mediterranean food. And so I apologize if that was ascension, but I thought that entire experience was hysterical. But nevertheless, the torus itself was so beautiful. So let's take a deeper look at this torus. So let's take this thing. So as you can see, there are 7 different colors on the sky, right? So we've got, so starting in the top center, we've got purple, orange, black, blue, green, yellow, red. Now, if I take this thing and I roll it over, I believe you should be able to see me as I do this. And for all you curious, I will send you the Mathematica code because it's a lot of fun. It's pretty nice. And if I flip it over, I see basically the same pattern, right? So if we follow one, let's follow the black. So the black starts up here and it comes in, and then it comes in through the inside of the torus and then back up around the other side. Okay, so my question is, so this is a map, right? I've divided the torus into these regions, and I just gave each region a different color because I could, and I'm in charge of this presentation. So my question is, could I have used fewer colors, right? Notice that there are 7 different colors on this torus. Let's go back. Let's look at that black thing. Okay, so my question, how many different states is the black state touching? So I can see right on this edge, I can see, what color is that? It's like a purple. Yeah, okay. So this black, it's touching the orange and the red, and I'm counting on my fingers, even though you can't see it, so up to 2, and the purple, 3, and the blue, 4. And okay, now I'm gonna follow the black. So it's coming up here, it's coming up here, it's gonna come pop through the torus and then around to the other side. Oh, and at this other end, it touches the green and yellow. That means that the black state touches all 6 other states. There's no other color that we could have used to recolor that one. So this map actually shows that the torus, that there is a map on the torus whose graph requires 7 colors, because there's no other color we could have used for that black state. All of the other ones are taken. And I think that's absolutely marvelous. Okay, so now let's cut back to my slides. Okay, wonderful. So we've said these graphs aren't necessarily going to be 4 colorable. The graphs aren't necessarily going to be planar because they're going to be like 7 colorable or something. And so what is this? What is this number? This number for the torus? But there's no reason that we have to stop at the torus, right? I mean, what if the globes lived on a 2-hole torus or a 3-hole torus or an n-hole torus or a Mobius band or something crazy, right? How many colors, and if you are a cartographer living on a 2-hole torus and you were scarred by your young childhood memories, your mother-in-law, or I guess, not childhood, but your memories of your mother-in-law just torturing you over coloring in these crazy patterns, how many different colors would you need to color in a map effectively on your toroidal world, right? We on Earth, because okay, Earth is almost sphere, so we only need 4 colors. If we lived on a torus, we need 7. But if we were on a 2-hole torus, I mean, how many would we need? And so, um, I I cannot prove these theorems for you because they're so hard and complicated. I can give you sketches, but that's the best I can do. And part of the reason is to bound these things, there's so much work involved, right? To show that this chromatic number of a surface is at most k, we have to reason that any map can be k colored. That sort of requires an algorithm, right? That no matter what the surface looks like, no matter what the map looks like, I can figure out a way to k color it. That's pretty strong. On the other side, showing that it is at least k requires the presentation of a single map, which we can prove is k colorable, but not k minus 1 colorable. The first part of that is pretty easy, right? You present a single map, like we did for the torus, right? We present a single map. We have to prove that it's k colorable, but we have to prove that it's not k minus 1 colorable. That can be a lot of work. Just ask the graph theorists about proving that things are not k minus 1 colorable. But it turns out you can do this. Ringel-Young's 1968, absolutely beautiful theorem. If S is a surface and its genus is M, then its chromatic number is the floor of 1/2 times 7 plus the square root of 48m plus 1. This is pretty nice. If you think about it for a second, if we increase m from genus 1 from the torus, which would give us the 7 that we have, if we increase that m up by 1, and it's going to increase that square root by from 7 up to something very close, but not quite 10. And then when we round out, it will continue to grow. So it's actually harder to color in maps on the 2-hole torus or the m-hole torus as m continues to get larger. And there are a couple exceptions, right? We've already said that this doesn't really apply for the sphere because the chromatic number is going to be 4, and the Klein bottle has chromatic number 6. And remember that this means this is an incredibly powerful theorem that any map can be done with this many colors, and there are maps which require this many. Okay. So I'm going to leave you, right, because I'm running out of time here, with a bit of global intuition about coloring, because coloring is just such a phenomenal property to me. It blows my mind every time I think about it. So coloring, it seems to me, it seems apparent that coloring is a pointwise condition, right? If I can color Swaziland blue or green or red, then the question is only what the color of Swaziland's neighbors are on the map. If the colors of its neighbors are good, then I can color Swaziland whatever I want, right? If not, that's a local problem. That's a problem with local interference, right? And that's true for both graphs and surfaces. But here's a remarkable theorem from Erdős in the 1950s. So if I take any choice of G and K, there's a graph with chromatic number at least K and girth at least G. We also have seen that any surface is locally R2, but it presents different chromatic structure. And so the link between these two things, right? So the first for the graph theory theorem, and I want to draw a little picture very quickly. Okay, so if I want to draw this little picture, so I have the wrong end of my pen, right? So what this is saying, large girth means that there are no small cycles. So what that means is that if I want to think about this particular vertex V0, I want to say, gosh, what can I color V0? And usually, right, the fewer things that are connected to V0, the easier it's going to be to color. And so maybe I have lots of things coming off, but I know by this theorem from Erdős that the smallest cycle is going to be very, very big. So locally, the graph is almost a tree. It's almost too colorable. This is getting a little bit deeper into combinatorics. But despite that fact, despite the fact that locally around V0, if everything is too colorable, globally, this thing could be 10 colorable. That's absolutely absurd. And you can increase that chromatic number as large as you want and the size of the girth. So no amount of local information is ever enough to tell you about graph colorability. At the same thing, imagine you were an ant, well, or a person, because I can only draw a person, and you were living on a sphere. And you said, gosh, what can I color this thing? Because we really are ants living on the earth. What can I color my maps with? And you say, oh, it's 4 colors. Great. Let's say that you were a person and you weren't woke enough, so you still believed the Earth was a sphere, even though you were really living on a torus, right? The CIA is keeping that one under wraps. So you're living on a torus. You look around you, you see the same things that the guy on the sphere is seeing, right? You're looking around, you're saying, hey, this looks pretty flat because it's a two manifold, right? It's locally homomorphic to R2. This is pretty good. But your maps need 7 colors. That's 3 more than the guy on the sphere did. That's absurd. There's some global information packed in here that is incredibly deep, and I think is just absolutely gorgeous. Okay, but that's it for new material. And so now I need to give you your homework problem. So here's a short little bibliography. There's the papers from Applenack and Rings and Young, and wonderful articles from MathWorld that are for some reason double printed there, but one of those is a hot link and one is not. Anyway, here are your homework problems. So the first one, and my presentation is over, so I think I'm within the time limit, but I want to read you these homework problems just in case anything isn't perfectly clear. So the first one, I want you to find a map on the Mobius band which proves the lower bound for its chromatic number, right? So I want you to find a map that requires a certain number of colors. And if you want to find that number, you can look it up on that Wolfram page that I have again linked there, again double linked. Remember for this problem that the complete graph on n vertices has chromatic number n. You can use that fact. And if you're having trouble finding the number in that Wolfram article, I will give you a hint that it rhymes with pix. Okay, so the next one, right? So prove that the graph depicted on the next slide, which of course you cannot see yet, is not planar using only the theorems discussed in this presentation. So I'm gonna hop over there. So here's my graph. Prove that it's not planar. You can do that using other graph theory stuff if you want, but you need to formally prove that it's not planar, and you can do it only using the theorems from this presentation. So I hope that this recording went well, and thank you for listening. Got to get rid of this thing now.